same criteria we discussed earlier. We saw before how only a few regular polygons could be put on the faces of those platonic solids. But can we connect these shapes to each other in the fourth dimension to create 4D dice? The answer is yes. In fact, every platonic solid in 3 dimensions has a 4-dimensional counterpart. Like if you join tetrahedrons together at 3 to an edge, you get the hypertetrahedron. There's also the hypercube, hyperoctahedron, hyperdodecahedron, and the hypericosahedron as well. But there is a 6th platonic solid that emerges in the 4th dimension, and it's the octacube or hyperdiamond. The analog of this constructed in 3 dimensions is the rhombic dodecahedron, something which is not a platonic solid due to the irregular faces. But in 4 dimensions, amazingly, the necessary criteria are all met. And you'd think it gets even crazier as we move up. But guess what happens in 5 dimensions? There are now only 3 platonic solids. When we move to the 6th dimension, there are still 3. And as we continue to go up, we unfortunately only find 3 platonic solids. Now, moving on, here's another example of something we know very well for up to 4 dimensions, but afterwards we know very little. And this has to do with kissing numbers, or the maximum number of unit spheres that can be arranged to barely touch or kiss another common unit sphere. For example, in 2 dimensions, the kissing number is 6. And that's because if you have a single circle, at most 6 other circles can be touching it in this way. This wasn't too hard to find, but in 3 dimensions it already got difficult, as it took mathematicians a while to figure out that in fact 12 is the kissing number. And after much more effort, we have determined that in 4 dimensions the kissing number is 24. However, for 5 dimensions, we don't know the kissing number. We just know, as of this video, that it's between 40 and 44. Then for 6 dimensions and 7 dimensions, we also only have a range of numbers it could be. But funny enough, we have figured this out for 8 dimensions, as the kissing number is 240. And even stranger, we have determined that in 24 dimensions, the kissing number is 196,560. It turns out something weird does happen in 8 and 24 dimensions when it comes to spheres, but I'll get to that soon. The last thing I want to mention about 4 dimensions, though, is that there are no knots like the ones we're familiar with in the 4th dimension. Well, other than the trivial knot, which isn't really knotted. The reason is because a knot can be thought of as a 1-dimensional string embedded in 3-dimensional space, as it needs that 3rd dimension to exist. You couldn't make a knot on flat paper without self-intersection. But remember how I said I could unknot something by having it essentially pass through itself, which I demonstrated by cutting it? Well, in the 4th dimension, a knot would be capable of passing through itself through that extra dimension, meaning it's not really a knot, it'd just be a loop in disguise, and in mathematics this is just the trivial knot, nothing that special. However, in 4 dimensions it would be possible to have knots made out of 2-dimensional sheets though. No clue what that would look like, but we need that difference of 2 dimensions in order to create a true knot. So using that same logic, we could technically knot a 3-dimensional object, but we'd have to move it through 5 dimensions to do so. And with that, let's now transition to something else interesting that happens in the 5th dimension, which goes back to the video I made about adding up all the volumes of even-dimensional unit spheres, which comes out to e to the pi for anyone who hasn't seen it. Many of you guys want more of an explanation, and the biggest thing to note is that since the series converges, that must mean the volume of these spheres gets smaller as the dimension goes up. For a 1-dimensional, quote, sphere, or really just a line segment with radius 1, the length is of course 2. A 2-dimensional sphere, or circle with a radius 1, has an area of pi, or 3.14. A 3-dimensional sphere with radius 1 has a volume of 4/3 pi, or 4.189. Then from the equation for the volume of an n-dimensional sphere, we can calculate that a 4-dimensional sphere of radius 1 has a volume of about 4.935, and a 5-dimensional unit sphere has a volume of 5.264. Notice that the number keeps going up with every dimension. But once we get to 6 dimensions, a sphere with radius 1 has a volume of 5.168. It's finally lower than the previous dimension. For 7 dimensions, it goes down again and continues to do so. If we look at the plot for the volume of a unit sphere versus the dimension we're in, we see that the 5th dimension is the peak, and it eventually does approach 0. But geometrically, why is that the case? Well, I'll give the best explanation I could find. In regards to 2 dimensions, let's say we perfectly rest a circle inside a square, which has side lengths of 1. Well, it turns out the circle takes up 78.5% of that square's area. When we move to 3 dimensions and put a sphere inside a cube, also with side lengths of 1, that sphere takes up only 52.3% of the volume. Adding the extra dimension decreased the ratio of those volumes. If we go to 4 dimensions and embed a hypersphere inside a hypercube, the sphere only takes up 31% of that volume. But notice that the cube's volume is not changing as we move up in dimensions. For 2 dimensions, the area of the square is 1 squared, or 1. In 3 dimensions, the volume is 1 cubed, or 1. And in 4 dimensions, it'd be 1 to the 4th, or of course 1. Yes, we are comparing completely different units, so it's not the best physical comparison, but the sphere is taking up less and less of something that always has a volume of 1. Thus, the sphere's volume will go to 0. Another thing to notice is the diagonals of the cube. In 2 dimensions, the diagonal has a length of root 2, while the circle has a diameter of 1, just a little less. In 3 dimensions, though, the diagonal of the cube goes to root 3, while the sphere's diameter again stays at 1. In any dimension n, the diagonal of the cube has a length of the square root of n, as in those corners get further and further apart without bound as we move up in dimensions. The sphere, on the other hand, is maintaining the same diameter, and thus taking up less and less of the space as the dimension goes up. Okay, now I know before I showed how the 5th dimension strangely has that peak volume, but actually this was nothing special, and that's because we were specifically using unit spheres. If we look at spheres with a radius of 3, the peak would happen at a different dimension. But since spheres with a radius of 1 are just so common, I decided to highlight it. Now let's look at sphere packing. For centuries, mathematicians have been curious about the optimal way to fill space using identical spheres. For example, in 2 dimensions, the question was, how can we arrange pennies on a table such that they are as dense as possible? And it turns out the best arrangement takes up about 91% of the space. For spheres, it was much harder, but we found the optimal arrangement takes up about 74% of the space. Now, for most dimensions higher than 3, we know very little about the best way to arrange spheres. However, as we go from dimensions 3 to 4 to 5 and so on, the gaps between the spheres start to increase from the 3D case. But for some reason in dimension 8, there are new gaps that are just large enough to hold spheres that can be perfectly locked into place, resulting in that optimal arrangement, which takes up about 25% of the 8-dimensional space. So we do know the math in 8 dimensions, and guess what? The math of optimal sphere packing was determined in 24 dimensions as well, just like the kissing number problem. By the way, for anyone saying, what's the point of this? It turns out sphere packing and the hypercube graph have applications in information and coding theory when it comes to correcting errors in data that show up in noisy communication channels. For example, let's say if I want to transmit the word yes to someone, I'll send them a 1, and if I want to transmit a no, I'll send a 0. Now this is simple enough, but errors could come up when it comes to long-distance communication. So instead, I'll send 3 1s for a yes and 3 0s for a no. That way, if an error does occur, like in a message that says 101, you can still say that's more likely to be a yes since 2 of the bits are a 1. Well, we can think of each possible message as a point in 3D space located on the corners of a cube. We'll put a sphere centered at the 111 message and one at the 000 message. If the radius of those spheres matches the length of the cube, then whatever messages they cover will be interpreted as the message at the sphere's center. Like here, the 101 message would be interpreted as the 111, or yes, since that sphere includes both of those corners. But if I want to include more words than just yes or no, I need to pack more spheres into the space. Yes, this example is pretty simplistic, but hopefully it shows how packing spheres tightly into space does have direct applications. And as we add more bits, we do the analysis on higher dimensional hypercube graphs, meaning we're dealing with higher dimensional sphere packing. Now let's see something weird in 9 and 10 dimensions. Imagine a square that is cut into 4 smaller squares, and then draw a unit circle in each one of those as shown. Then draw another circle in the center that is tangent to the 4 others. You'll notice that center circle is pretty small relative to the entire square, and is far from the edges. We'll do the same thing in 3 dimensions, which would involve a cube being cut into 8 pieces, and those each being filled with a unit sphere. Then we'd pack a sphere in the very middle, such that it barely touches the other 8. Here you'll also notice that the sphere is much smaller than the cube. But as the dimensions go up, that central sphere gets larger and larger, and in 9 dimensions, that central sphere actually touches the edge of the 9-dimensional cube. Then in 10 dimensions, it breaks through the sides of the cube, even though the cube, well, looks like it should be the boundary of the inner sphere holding it inside. However, when the sphere breaks through the cube, it still has a smaller volume than the cube. That is until dimension 262. After 262 dimensions, the hypersphere becomes larger than the hypercube, volume-wise. Okay, don't officially quote me on that, as I found it in various forum posts rather than an official source, but once I came across that information, I really couldn't exclude it. Now let's look at an example that's kind of similar to the sphere packing we saw earlier. Let's say we have a bunch of oranges, or spheres, that we need to wrap using